In this second part, we'll continue our discussion of magnetic fields. We have seen in previous slides from Ampere's law that Ampere's law states that the curl of H is equal to J, but when there is no current in certain regions of space, so when you don't have a current, the current is somewhere else, then curl H is equal to 0 because there is no current at this specific point in space. And as we know from the vector identity that the curl of the gradient of any function is 0, so this means that any vector whose curl is 0 can be written as the gradient of a scalar function. So here we can define using an approach very similar to what we do in electrostatics, something that we call magnetic scalar potential, which is Vm, and H can be defined as minus the gradient of Vm. So this will be another means by which we can calculate the magnetic field. Of course, this is valid only if you don't have a current in the region. If you have current, then the curl of H is not 0, and the H cannot be written as minus the gradient of Vm. If it can be shown that this magnetic scalar potential also satisfies Laplace equation in a very similar way to what we had in electrostatics, as long as there is no current. But this magnetic scalar potential does not find wide applications. The one in calculating fields and estimating fields, the one that's used very often is called magnetic vector potential, A. It has a symbol of A. This is the one that's really used very often in antenna theory and in other applications for calculating magnetic fields. So what is a magnetic vector potential? Because the divergence of B is equal to 0, we can write B as the curl of another vector A, and this A is the magnetic vector potential. I will show you now a derivation. I will follow the same derivation that's in the book of Sadiku about how to get this for starting from the Biot-Savart law. We know from the Biot-Savart law that the magnetic field H at any point is equal to the integration of I dl cross R over r squared here, 4 pi. This is the expression for the Biot-Savart law. And what we're going to be doing, we will show that this unit vector that you have here, this unit vector, which is a unit vector pointing from that infinitesimal current element of length dl to the observation point B, we show that this term here, which is this unit vector divided by this length squared, so the length from the observation point of that, from the observation point B to the wire, to that infinitesimal wire element, it has a length dl through which a current I is flowing, and we call the center point here as Q. And I will show you that this will simplify a little bit the analysis. I will show you that this term here is nothing but the minus the gradient of 1 over r QB. So if you take the gradient of this vector of this distance r QB from r to pointing from Q to B, so this distance here r QB relative to the coordinates of Q, not to the relative to the coordinates of B, relative to the coordinates of the observation point. So it should be very clear. I'm here differentiating relative to the x, y, and z of B, not relative to the x dash, y dash, and z dash of Q. So remember, this gradient here is really derivative relative to the coordinates of the observation point B, not of the source point Q. So this derivation is given as well in detail in the book of Sadiku. I will go over it just for people who will be interested to know it. So the length from the observation point B to that element is the length from the point P to the point Q. We can call the coordinates of the point B xb, yb, zb. The coordinates of the point Q, xq, yq, zq. Of course, we can call this one x, y, and z. We can call this one x dash, y dash, and z dash. What I want you to understand here is that we have an observation point B. It has its coordinates. We have a source point at the location of that current element Q, and it has its coordinates. So the vector pointing from from Q to B is equal to RP minus RQ, which is the vector RQB, this one here. The length of this vector is simply the square root of the square of all its components. Now, we'll differentiate this vector relative to the coordinates of the observation point B. So, I will show you how we can do that. Let's first take the gradient of 1 over RB. Remember, RB is nothing but this square, this R, this distance, nothing but this square root here. So when you differentiate the square root, then you say it's 1, or you differentiate 1 over a denominator, you say it is the square of the denominator, and then you multiply by the derivative of the denominator relative to the coordinates. And this is what we have here. The derivative of 1 of RB is minus 1 over R squared, so the distance squared, multiplied by the derivative of the distance relative to all components. Remember, we are getting the gradient of a scalar function. Then we are differentiating the scalar function relative to x, relative to y, relative to z, with each one of them in its respective direction. So now, how we differentiate this square root? It's the denominator. Of course, this will give you the square of the square root, and then you differentiate every term. The derivative of this term will give you 2 multiplied by xp minus xq, and then you differentiate relative to the parameter xp, and this will give you here 1. So you see that the result that you will get from differentiating rqb relative to xp only will give you this term. And of course, in a very similar way, if I differentiate this rqb relative to yp, I will get yp minus yq over rqp. And if I do it relative to z, it will be exactly the same thing. So now if we put all this together and we integrate it with this expression, we'll see that we have here the vector divided by its length. If you put all this together, this gives you the vector rqb divided by its length, so divided by rqb. So this will give you a unit vector in the direction of aqb. So now we know that the gradient of 1 over rqb, the distance between the observation point and that current element, is nothing but minus the unit vector pointing from q to p divided by the distance between them squared. This is coming from these 4 lines here. So this, I will show you how this simplifies the analysis a lot when we calculate our magnetic vector potential. So now I will go back to the Biot-Savart law. I will get rid of this term, and then I will replace it by minus the gradient of 1 over rqb, and I will use a vector identity, and this will simplify the analysis a lot. So we go back to the Biot-Savart law. We replace the unit vector divided by r squared, we replace it by the gradient of 1 over rqb with a negative sign. And now we apply this vector identity. This looks like now scalar, so forget about this scalar here. It's a vector cross the gradient of a scalar function. There is a vector identity that says that a vector cross the gradient of a scalar function is equal to the scalar function multiplied by the curl of the vector minus the curl of the scalar function multiplying the vector. So we apply this rule. This is this part here. This is what we have here. This is f is dl and v is 1 over rqb. Then I can expand that into two integrals. The first one is 1 over rqb multiplied by the curl of dlq, and then minus the curl of 1 over rqb multiplied by dl. And this is what we have here. So I got rid of this term and I replaced it by these two terms. Now, this one here, this curl, is derivative relative to the coordinates of the point B, of the observation point. But it has nothing to do with the point Q. Point Q is my source point where the current is. So this will give us 0, and only this one will remain. A minus sign will cancel with a minus sign. Then we end up that B is equal to the integral of the curl of this quantity. But remember, we're carrying out an integral somewhere in space. So there's some contour in space, and the current is somewhere else. So here, this curl operator has nothing to do with the integration. It's a completely different story. You are doing a curl after you carry out the integral, so I can carry out this curl outside the integral. I do not really have to keep it inside. I can carry it out because it's independent of on the point of the integration. Okay, so when you do that, this will show you that B is equal to the curl of this quantity, and this quantity is what we call A. This is the magnetic vector potential. Magnetic vector potential is mu I dl over 4 pi r qb. So in order to calculate the magnetic vector potential at one point, if you have a current I, what you have to do, or let's call a current dl, an element dl carrying a current I. What you have to do, you have to determine the distance to the observation point. We call this one r, and in that case, if there is a current I flowing here, the A is mu I over 4 pi r multiplied by dl. Remember, there is no cross product here. A in the same direction as the current, the same direction as dl, which is very interesting because A, it's a vector, is obtained by integrating dl. So it will have the same direction as the current. So to summarize what we have achieved that B, we have seen that B now is equal to the curl of another vector called A, and A is obtained by carrying out this integral for line currents. You integrate I dl over r. Okay, you integrate over the contour. It doesn't have to be really a closed contour. You integrate over the contour of the current. And the same thing, you can obtain a similar expression because we agreed I dl is ampere meter. So this is exactly equivalent to K over R. This is this one here, actually this ampere meter by meter. This ampere meter by meter. So it's ampere. So this would be exactly the same thing that we have here. Ampere per meter divided by R give ampere per meter squared multiplied by meter squared, you get amperes. The same thing is happening here. Ampere per meter squared divided by meter and then multiply by the volume, then you get ampere again. So what I'm trying to say here, you can calculate the magnetic vector potential for current, for line currents, for sheet currents, but you have here to carry out surface integrals. You can carry it as well for currents flowing in volume, J, but you have to carry out a volume integral. And this is very similar to what we had before for the magnetic vector potential. For the electric scalar potential, we're able to obtain the expression of V for point charges, for surface charges, and for volume charges. If you don't worry about the derivation of A, what I want you really to understand that B can be written as a curl of another vector, which is a magnetic vector potential. And this magnetic vector potential is the nice thing about it is that it is in the same direction as dl. You can see A and dl are in the same direction. So if you have a wire in the z direction, A will also be in the z direction. This is a great thing about this one. And once you have A, from A you can get B by applying the curl. One last thing to mention about the magnetic vector potential is that we have already defined that the magnetic flux density over a closed surface is equal to 0. There is no magnetic flux lines are not created on points. They are not diverging, they are not converging, they are closed lines. But if you integrate over an open surface, then the integral of B dot ds, we can replace B by curl A. B is equal to curl A. And this will give it the integral of curl A dot ds. And here, if I apply Stokes theorem, I can convert this one into integral over the closed contour surrounding that surface. Because remember, if you have a surface S, like this one, this is a surface S, okay, this surface S, then it is surrounded by some contour L. So if we apply Stokes theorem to this part here, we can see that the flux can be obtained as a closed line integral of A. So now we have two ways to calculating the magnetic flux. Either you integrate B dot ds directly through that surface, and what you will do, you'll calculate the total flux coming out from that surface by B, or what you have to do, if you have A, you can integrate A around that closed contour surrounding the surface, and this will give you exactly the same answer. Now let's have some examples. We have here first a current element of length L carrying it's a linear current carrying it has length L, it's carrying a current I in z direction. would like to show that at a very far point, A is given by this expression, mu naught I L over 4 by R in the Z direction. We agreed that the current, because the current Z direction, A will also be in the Z direction. This is one of the nice things about this magnetic vector potential. Now, after you have done that, we would like also to get B. B, of course, is equal to the curl of A. So we first have to get A by applying that integral expression for wire currents, and then we can get B as curl of A. So the expression for A for wire currents is A equal to mu naught I dl over 4 by R. Now this is dl. This is our L. It's a wire carrying element, and we want to get A very far from it. But very far, this element looks like a tiny differential element. If you are very far from the wire, this looks like, even though it has a length of L, which can be significant close to it, but when you are far, it looks like a tiny differential element. In that case, I don't have to carry out an integration, because I'm not integrating any differential elements. It's just one differential element. So I can take this one out of the integral and replace dl by L Az. It has a length of L in the Z direction. Then it's very simple. We can say that A in that case is mu naught I L over 4 by R in the Az. And remember, R is the distance between your current to the observation point. And here, in this case, if I take this one as the origin, then R, which is this distance, can be written as Z squared plus rho squared. And this is what I did here to put everything in terms of cylindrical coordinate systems. So we now know that this is the expression for A. Now, can I get B? Yes, we can get B. Of course, from our calculation, we can expect B to be in the phi direction, because the current in the Z direction, as we have predicted earlier from the Biot-Savart law. So what we'll have to do, we have to take this A and apply its curl, and this will give us a vector B. So now if you take the curl of A, remember A has only one component, which is Z. The curl will give you six derivatives. I will keep only two of them, the one related to Z. So we differentiate Az relative to phi in the rho direction, differentiate Az relative to rho in the phi direction. Az is not a function of phi, so this also will give us 0. So only this term will remain. So we have to differentiate. This is Az here. We have to differentiate it relative to rho, and then we multiply by a negative sign in the phi direction. Of course, if you differentiate this one, this is a bracket to the power minus 1/2. So it gives you minus 1/2 multiplied by the bracket power minus 3 over 2, and then you multiply by 2 rho. So this is what you do here, and this will give you here the expression for this one. So 1/2 from the derivative cancels out with the 2 coming from the derivative of rho squared, and the negative sign coming from here cancels from the negative sign coming from the minus 1/2. And they end up with this expression for B in the phi direction as predicted. So indeed, B for a length of wire of length L far from the wire, still in the phi direction, and is given by this expression here. We consider also this example. Here we are given the magnetic vector potential. There is some current distribution, and this current distribution created this magnetic vector potential. A is 15 e to the minus rho sine phi Az Webers per meter. The units for A I forgot to mention, it's Webers per meter. Because when you differentiate relative to when you differentiate it to get its curl, you are actually dividing by another length, so it becomes Webers per meter squared. We'd like to find H at the point 3 by over 4 and minus 10, and of course this is given cylindrical coordinates. This is rho, this is phi, and this is z. We'd like to calculate the flux through the surface, rho equal to phi between 0 and pi over 2, z between 0 and 10. So we'd like to calculate the flux through a part of a cylinder whose radius is 5, and phi is spanning an angle of pi over 2, and z is the length of 10. So for this problem, it's pretty systematic. We have A, we can get B from A, and then if I divide B by mu naught, then I have H, and then I can get H at any point. And then if I want to get the flux through the cylinder, I have to integrate B dot ds over this 1/4 of this surface of this cylinder. Here in this problem, we have only AZ, and the AZ is a function of phi and rho, both of them. We don't have any other components of A, so this is why all other components of curl are 0. We just did not list them. But there are 6 derivatives of A. If you differentiate the sine relative to phi, you get cosine phi. So this term here gives you 15e to the minus rho over rho cosine phi a rho. If you differentiate this term here, e to the minus rho will give you minus e to the minus rho. So this minus becomes positive, and you get 15 e to the minus rho sine phi a phi. So we differentiated now b, we got now b, so b now has 2 components. And because h is parallel to b, they are in the same direction, h will be equal to b divided by mu naught. Remember, if I don't mention for you the value of mu, you should take it as mu equal to mu naught. So now we have h, we can calculate h at any value. We were given certain value of rho equal to 3, phi equal to pi over 4. At pi over 4, this will give me 1 square root 2. This will give me 1 over square root 2. This term here will give me 3. So I can calculate h at the given point. And remember, this expression is not a function of z. So the z coordinate does not matter. So at the requested point, I put rho equal to 3. I put phi equal to pi over 2. Both the cosine and sine will give me 1 over square root 2. I took it out. Rho e to the minus rho will give me e to the minus 3. 15 is still there. I divided by mu naught, so I divided by 1 4 by 10 to the minus 7. I took 10 to the minus 7 to the numerator. It became 10 to the 7. If you simplify all this, you get this expression for the magnetic field. The rho component is 1/3 of the phi component. 14 a rho plus 42 a phi 10 to the power 4 ampere per meter. Now if I want to get the flux, I'm integrating over the surface of a cylinder bar to the surface of the cylinder. The unit normal to that surface is a rho, and the unit area here is rho defined in this direction and dz in this direction. So we integrate very straightforward integral of b dot ds. This is b, and remember here I kept only the rho component of b. I didn't care about the phi component because my surface has a unit normal in the rho component. So I kept only b rho multiplied by ds in the rho direction. So now we do that. Rho will cancel with rho. The integral of dz is from 0 to 10, so it will give you 10. The integral e to the minus rho, you put rho here equal to the size of the cylinder, and then you integrate cosine phi. The integral of cosine phi will give you minus sine phi. So you put all this together. You can see I replaced z, I integrated z, I got 10. I put rho equal to phi, so I got e to the minus 5. The integral of cosine phi will give me sine phi, and sine phi here, you put upper limit and lower limit. The one that's will give you a value here is the upper one, so it will give you 1. So this will give you 150 multiplied by e to the minus 5 Webers, or 1.011 Webers. So the total flux coming from that surface is 1.011 Webers. And you can see here, once we have A, we can get B through the curl of A. And once I have B, if I know mu, I can get H. I can get the flux coming out from any surface, and so on.